G'day guys, in this video I'm going to be showing you how to solve a fairly challenging relative motion problem. And it's challenging because not only do we have to solve for the velocity of this slider, that's the velocity of A, but we also have to find the acceleration of our slider, right? And because this is going to be such a challenging video, I'm going to split it into two separate parts. I'm going to do part 1 dedicated to finding the velocity and part 2 dedicated to finding the acceleration. Okay, so I recommend you pause the video, have a shot at yourself first, then come back when you're done. Okay, well hopefully the first thing you try to do before anything else is simply solve for the angles and distances that you think we might need. So right now we know r is equal to 0.1 meters, and we know that L is equal to 0.2 meters, so I'll substitute those values in. We know this is an angle theta, which is given as 45 degrees, and I'm going to call this an angle gamma. And let's try and find gamma. Well, we can do that using the sine rule, and we can say that sine theta divided by 0.2 is equal to sine gamma divided by 0.1. And you can solve for this using pretty easy algebra techniques. And you can say, well, gamma is going to be equal to 20.7 degrees. Hopefully you got that far, but if you didn't, that's okay. Just pay attention. I'm going to be showing you how to do this step by step. So the next thing we're going to be doing is trying to find the velocity of B. And you might be asking to yourself, well, hey, why are we trying to find the velocity of B? After all, we're trying to find the velocity of A. And the reason we want to find the velocity of B is because we need to work our way towards point A. We're given a whole lot of information about OB. We need to work our way towards there. Okay, so that's the game plan. So let me write down a relative motion formula we're going to use. We're going to say that the velocity of B relative to O is going to be equal to the velocity of B minus the velocity of O. Okay? We're going to be using this formula. Now this is a pretty easy formula to analyze, especially in this case, because the velocity of O, right, that's this point, is actually 0. Right? The pin isn't moving anywhere, so that means the velocity is 0. This is probably a good time to specify that I'm using this axis. I'm considering horizontal to be positive to the right and vertical to be positively upwards. Okay? So let's evaluate this term just here. And I find that the easiest way to do this is by actually drawing the link over again. So let me just quickly draw link OB. This is going to be link OB just here. Now I think you'd agree with me that the velocity of B relative to O would be under circular motion. So B relative to O will be undergoing circular motion, and to make that a little bit clearer, let me just draw this circular path just here. Now we also know its angular velocity is in this direction, which means that the velocity of B relative to O must be tangential to our circular path, which would be in that direction. Once again, this is the velocity of B relative to O. Okay? Now let's actually shove some angles in here. We know that this right here is an angle theta, which means that we know that this angle here is an angle theta, which means that we know that this angle here is an angle 90 minus theta. Okay? Now we're ready to get started on the harder part of this. What is the magnitude of our relative velocity vector just here? Well, because it's undergoing circular motion, that means we can use circular motion formulas. We know that the magnitude of this velocity is going to be r omega, which in this context is going to be equal to 0.1 times by omega. So it's going to be 0.1 times by 5. And the horizontal component of that is going to be equal to 0.1 times by 5 times by cosine 90 minus theta. That's the horizontal component of the velocity of B relative to O. And because it's the horizontal component, I'm going to times it by the I unit vector. Now what about the vertical component? Well, it's going to be 0.1 times by 5, that's the magnitude, times by sine 90 minus theta. And of course you times it by the J unit vector, right? Now of course that is in fact equal to our right-hand side, which is just equal to VB. So let me say that is equal to VB, right? This is all one expression. This is equal to VB, right? Now let's actually evaluate the left-hand side of this expression. Well, we can say that VB, so that's the right-hand side, is going to be equal to this beast, which is going to be, when you plug into your calculator, this term will turn into 0.3535. And this term, when you plug it into your calculator, is going to be also 0.3535, coincidentally enough. and that's going to be meters per second. Okay? So we know that the velocity of B is going to be equal to 0.3535 meters per second to the right and 0.3535 meters per second upwards. Okay, so far so good. Now let's find the velocity of A. We're finally ready to approach this. Well, we can use the other circular motion formula. We know that the velocity of A relative to B is going to be equal to the velocity of A minus the velocity of B. Okay? Well, what is the velocity of A relative to B? To do this, let me draw link AB again, because I really think that helps. It's going to be a slightly longer link, right? 0.2 meters to be precise. This is going to be point B, and this right here is going to be point A just here. Now, I think you'd agree with me that the point A is going to move out a circular path relative to point B. So to make that a little bit clearer, let me once again superimpose this circular path just here. Okay? Now, I have no idea whether this link is going to undergo whether it's going to be going in a clockwise direction or counterclockwise direction. I'm just going to assume out of the blue that it's rotating in the clockwise direction. I'm going to call that omega AB. I'm assuming the link is rotating clockwise. That is an assumption. We'll test its validity later. But based off this assumption, I'm forced to accept that the velocity of A relative to B will be tangential to this path in this direction. This is going to be the velocity of A relative to B, right? And to make that a little bit clearer, this right here is our vertical, this right here is our horizontal. Let me get rid of A right here. This right here is point A, just there. There we go. Okay, well, we know this right here is an angle gamma, which we recently calculated, right? Which means that this angle here is 90 minus gamma, which means that this angle here is gamma. Nice and easy. Now, we know that the velocity of A relative to B is going to be equal to r omega, which in this context is going to be equal to 0.2 times by omega AB. So this is going to be 0.2 times omega AB, right? Now, what is its component in the horizontal direction? Well, because it's to the left, it's going to be negative. It's going to be negative 0.2 omega AB times by sine gamma. Now, what is the component of VAB in the vertical direction? Well, it's going to be 0.2 omega AB times by cosine gamma, right? I've just deconstructed this triangle into vertical and horizontal components, noticing that it's traveling towards the left in the horizontal component, and that's why it's negative. Okay? Now, what is VA? This is the velocity of your slider, right? Now, we have no idea what the magnitude is, but fortunately from the geometry, we can tell that it must be to the right or to the left. I'm going to assume that it's purely to the right. This is just another assumption out of the blue, and I'm just going to write this as VA is going to be equal to some magnitude, which I'm going to write as VI without the arrow, 0 just here. Okay? And of course, that's subtracted by VB, which is this. So let me just make some space just here. Okay, there we go. I've just made a little bit of space and written in VB, which we calculated here. Okay? So this is this expression just here with our values expanded out. Now you might be wondering, well, hey, how do we solve for VA here? Well, it's actually quite simple. We can actually just equate the J units and the I units. Right? So let me break this to you step by step. Let's equate J values. Right? So in case you don't know what that means is we just focus on this bottom row equation. We're saying 0.2 omega AB cosine gamma is equal to 0 minus 0.3535. That's all it is. And we can solve for omega AB that way, and we can say omega AB is actually just going to be equal to minus 1.8897 radians per second, right? Now this negative is important, right? First of all, we assumed that omega AB was clockwise, so we have to stick to that convention and say this is clockwise, but because it's negative, that just means that our assumption was wrong all along, and in fact, this thing is actually counterclockwise. Nonetheless, I'm still going to substitute our value of omega AB as negative 1.8897, right? Now let's solve for VA. We know that VA can be found by equating I values. So let me really reiterate this. Let's equate I values, right? And of course that just means we focus on this top row, right, and solve it. And you can, because now we know omega AB, we can solve for VA, and we can say VA is just going to be equal to 0.48714 meters per second. Okay, now this is the magnitude of VA. Is it to the right or is it to the left? Well, let me just reiterate that this is our velocity vector of A, and we said that our velocity of A is equal to some magnitude, VA without the hat, times by I. I is to the right. Because this is positive, that means the slider is moving to the right. That's really crucial, okay? Because this is positive, that means this thing's moving to the right. So let me just reiterate this right here. The velocity of A is going to be equal to 0.48714 meters per second in the I direction, which is to the right. That is the first part of this done. Tune in for the second part where I find the acceleration of the slider. It's going to be very challenging. Strap yourselves in.